Hey everybody, welcome to the first episode of 2022 and featuring today's guest, my friend Carlo Rovelli, who's joining us all the way from Toronto in this particular video. And currently I think he's back in France, where he is a renowned professor and scholar of quantum mechanics and of the theory of time, space, matter, energy. And it was a treat to interview him. This was, again, something I need to beg his forbearance and your forbearance. An interview I conducted, 6 or 7 months ago by the time you're listening to this, and just had so much cool content to put out and needed so much kind of investment to give this episode the attention it deserved that it got delayed. And not the least of which was the recording that Carlo and I have been doing since middle of last year in 2021 of Galileo Galilei's dialogue on the two chief world systems. So look for that coming extremely soon, hopefully in time for Galileo's birthday, the first ever audiobook ever made of Galileo. It's kind of impossible to believe. And when I first heard that remarkable stat that no such audiobook existed for the maestro, I became quite enervated, and it inspired me to seek out and hopefully not destroy this wonderful manuscript by one of history's greatest thinkers, but also one of history's greatest writers. And Carlo was the ideal person to land in the starring role of Salviati, the salvation, the chosen one. But anyway, you'll have to wait for that. This episode's about his most recent book, Helgoland, which is a story of another genius. In this case, it involves the story of quantum mechanics and how quantum mechanics came to dominate what we understand about the world. So what is Helgoland? Helgoland is a phenomenal kind of magical quest. I call it a hero's journey. It's really tracing the journey of how Werner Heisenberg made critical understanding of how we could conceptualize and formalize quantum mechanics, and he did so in contrast as most heroes have to have. There has to be a conflict, in addition to the protagonist, sort of an antagonist. And I wouldn't say that Schrodinger is Heisenberg's antagonist, but this the story traces this isolation that Heisenberg had to go into on this isolated treeless island in the North Sea, where this young guy who's 23 is the age of my students. And he set the stage for everything, that we do in modern quantum mechanics is, in some sense, tracing its evolution from what was discovered on Helgoland, this remote island, not Legoland. We have that here in California. I've made some discoveries there, such as why are Legos so much more painful at night than in the morning when you step on them. But that's for another subject. This topic, we talk about what is a matrix, what does it mean to do matrix mechanics, how can we understand philosophically based on pure math, how can pure math lead us to a philosophical understanding of the interpretation of quantum mechanics. So I devoured this book. It's got many glowing reviews. This book has an audiobook version, which was not read as his last book, The Order of Time, which I interviewed him about last year by the time you're listening to this in 2021. By Benedict Cumberbatch. There are no Cumberbatches narrating this episode, this particular book. But better than that, we just keep witnessing the maturation of one of our greatest current thinkers, who happens to be a great writer as well. And so I couldn't be more pleased that I'm working together with Carlo and one of my oldest and best friends, Lucio Piccirillo at the University of Manchester, Jim Gates at Brown University, reading the foreword of Galileo's dialogue, and also Fabiola Giannati, who's reading Galileo's own author's preface to this audiobook, and then finally Frank Wilczek, who reads Einstein's foreword to the dialogue. But anyway, you'll have to wait for that. Hopefully by February 15th or so, I'm going to launch a new podcast. Think Like Galileo or something like that, or the dialogues. Hope to have some great guests on the show as well. I'm going to try for some stretch guests, but definitely try to get on all my fellow co-authors, Carlo, Fabiola, Lucio, Jim Gates, Frank Wilczek, and maybe a couple of surprises, because Galileo is more relevant than ever now. This book is 390 years old in 2022. So anyway, this book that you're going to hear about as soon as I stop yammering on, Helgoland, is another book that will bring to life in a way, as Neil Gaiman wrote in his encomium about it. This is the place where science comes to life. Rovelli is a genius and an amazing communicator. And that's true, and you'll see it in this book. We also have a little callback to my episode with Carlo's nemesis, perhaps his antagonist, Michio Kaku, past guest on the show, when Kaku had some negative things to say about, not about Carlo, but about loop quantum gravity, which Carlo, among others, has done more perhaps to popularize than any other person. So anyway, I'll stop yammering. I'll save you the normal spiel about leaving reviews. Now you can leave reviews on Spotify, so please do that. If you're listening on that platform, you just leave a rating. You don't even have to write a review, actually. And you can do the same on Apple Podcasts. And you can also do it on Audible Podcasts. So I do it on all three. And I would be delighted if you would do the same. And now, without further ado, please enjoy this episode featuring Carlo Rovelli, my friend and co-author or co-narrator, about his wonderful new book, Helgoland, Making Sense of the Quantum Revolution. Let's go.
Any sufficiently advanced technology is indistinguishable from magic.
Open the pod bay doors, Hal.
Welcome, everybody, to a special segment with Professor Carlo Rovelli, who's a friend, a hero, an adventurer, and an explorer of mental realms beyond which many of us can contemplate. Today, he is coming from the island of heroes, the island of physics, which is also not unrelated to the island that plays a huge role in his magnificent new opus, Helgoland. We'll talk about that in this segment. First of all, Carlo, how are you, and where are you, my good friend?
Hi, Brian. It's a great pleasure to be with you. I am in a fantastic place. I'm in a Greek island in northern Greece. Actually, it's almost Turkey. I can see Turkey there from the window, called Lesbos. And Lesbos is a magic place because you can say it's the beginning of poetry and the beginning of science, maybe exaggerating a little bit. Because here is where Sappho wrote his poems. Sappho lived, and Alcaios, two immense Greek poets, and I'm reading their poems, and they're marvelous. But here is also where Aristotle spent many years doing his biology, and people say the Lesbos was for Aristotle what the Galapagos were for Darwin, but it's more than that, because Aristotle biology is probably the first specific, detailed campaign of observational science, collecting data, talking to the fishermen, talking to the people, making catalogs, comparing things. It's really the beginning of observational science here in Lesbos 25 centuries ago.
That's wonderful. And when I think about Greece, it's impossible not to think about the Odyssey, Homer, the great heroes of Greek mythology. But also, as I think about it, the role of islands plays a huge role in science, as you say. You mentioned Darwin, the Galapagos Islands. We have here in America a shelter island where Feynman and many of the greats would gather in the 40s and 50s under government security protection. Their brains were so valuable that the military would come with guns, Carlo, to protect them. And of course, you mentioned Lesbos, where I think Aristotle did do observations. And I think he was the first in human history, Carlo, correct me if I'm wrong, to determine that whales are mammals and not fish. And he probably did that there.
Yeah, and his science is extraordinarily good. Aristotle has a bad press as a scientist, but it's completely undeserved. He's an immense scientist.
So with the laws of logic and just really, creating some of these frameworks, of course, you've mentioned in the past in other conversations we have about Anaximander and others that you regard similar status as heroes. But I want to talk now about an island that really is unheard of until this wonderful new book of yours, Helgoland, came out. And that's Helgoland Island in the North Sea, which is a barren, tree-swept island where a romantic tale of a 23-year-old went into seclusion and came out with some revolutionary new ideas that upended the orthodoxy of his time, similar to what Darwin did in his heroic voyage in the Beagle. Talk about this marvelous island, Helgoland, what it means. And I'm curious, have you been there?
many years ago, and I want to go back because now after being immersed in Helgoland thinking for so long, for writing this book, I definitely want to go back. This happened 100 years ago. In fact, 98 years ago, 97 years ago. And it's really one of the moments of the great revolutions in science, one of the greatest revolutions in science. Some might say the greatest, which is the beginning of quantum theory. It's the beginning of quantum mechanics. Not because quantum mechanics was entirely invented there. Quantum mechanics came in many steps. But that, up to that point, were the bits and pieces of new information about the world that didn't fit together. And this young kid, because he was 23, isn't marvelous? Werner Heisenberg, German, went to this island to immerse in his calculations, but really because he was suffering from hay fever and the island has no vegetation. So it was a relief for his allergies, and spent days and days there and came out with this incredibly new idea, which was the turning point of that opened up quantum theory. In fact, Heisenberg is the one who got the Nobel Prize. He's the only one who got the Nobel Prize for the creation of quantum theory, and deservedly so. And the idea was there. He was alone, this magic island. The name Helgoland means sacred island. Goethe says is one of the places where you hear more intense the spirit of nature. I don't know if this is true, but certainly it's a place where our view of the world changed. Heisenberg did something completely new. And it's fantastic because we're still immersed in that revolution, right? The quantum revolution, this, from the point of view of science, this is probably the center of the quantum revolution. Like the Renaissance was the period of the Copernican revolution. Matter is not the same. Reality is not the same after the quantum. And a century has passed, but still, we're still debating among ourselves what we really have learned with quantum physics. In spite of the fact that, the technology we're using is quantum physics. We understand the atomic structure with quantum physics. We understand the color of the sky. We understand how the sun works. We understand everything with quantum physics. Has never been wrong. All the prediction of quantum theory, all right. We have no idea where there is the limits of quantum theory. So it's the greatest theory ever, in a sense. And yet it's confusing, mysterious. And that's the beauty. And it all started on that island.
And when I read your words, they're so full of poetry and beauty. But you also say in this book that it's a book for your colleagues. And I hope that includes me, because it's not a simple book. It's not a dumbed down. You never do that. You respect your audience too much, and you're rewarded by millions of fans around the world, including having your books translated more times and sold more copies than 50 Shades of Grey, which, I was a customer for both of those books in that rare cohort. But Carlo, you talk in the book, you talk about granularity. And you talk about Heisenberg as this link between the granular, between the atomist, between the ancient Greek, Lucretius, and Latin scholars. And I want to know, when you think about this, the difference between what we can observe and what really is. That really came home to me for the first time as a professional physicist in this book. That, as you say, Bohr, Einstein used to say God doesn't play dice. Bohr said, don't tell God what to do, Einstein. But I feel like we kind of sometimes are guilty, and that we tell the particles what to do. And we tell them they should behave like little baseballs, and so that we can understand them. Talk about what Heisenberg meant to our reinterpretation of mechanics as a whole.
You touched the core problem, because what Heisenberg did exactly on that island, it's the following. The problem at the time on the table of the physicists was how the atom works. And it was understood roughly that the atom is this central nucleus that later has been much better understood, around which somehow there are electrons. But these electrons around the nucleus, like planets around the sun, seem to do very strange things. They were only orbiting on some specific orbits and then jumping from one orbit to the next. One orbit and then they jump down to another orbit. The famous quantum leaps. These are the first quantum leaps. And nobody understood what kind of force can move an electron on specific orbits and to these jumps, or which equation of motion can do that. And Heisenberg, this is completely magic. He said, forget the force. Forget the equation of motion. Keep the equation of motion you had before. Keep the force you have before. Keep the Hamiltonian you have before. Keep the description you have before. Change the way you think about the electron. It's not a little particle that jumps. It's something else. What is it? Don't ask. Just ask only what you observe. You don't see the electron, because to see the electron, some light should go from the electron to you. Just talk about the final observation. And this seems against science, right? I mean, it seems to be putting in doubt the entire idea that you describe what happens out there. You only talk about the observations. But it works, because he used this mathematics of the observables, and it fantastic works. And 100 years later, we all do that. I mean, every time the people who design this computer here and the hardware use essentially the mathematics of Heisenberg of what you observe. And you treat everything like a closed box. So I do this and I observe that. I do this and I observe that. But what does nature care about who observes what, right? What is the observability here? What is an observer? It's not a piece of nature like any other. And so today, everybody uses quantum mechanics in chemistry, in astrophysics, in nuclear physics, in all sorts of disciplines. And many people don't ask questions, but those who ask questions, what is really going on between one observation and the other? What happened in between? They split in various interpretations of quantum mechanics, which has mean different ways of trying to make sense of that. And some people, and my book comes right in the middle of this discussion, right? And some people say, okay, there's things going on there. There's a wave that fills up everything, and then out of the wave, in some way, we have the observation. But there is a different way of doing that, a different camp, if you want, which make the following observation. If I see the electron, I am a piece of nature, right? You're a piece of nature, Brian. You're not outside nature. And whoever is listening to us, the person observing is a piece of nature. It's not outside nature observing nature. So what quantum mechanics describe is not how a man or a PhD student observes nature. It's how one piece of nature affects another piece of nature. So that's the way to think about reality. Not how things are, not how one thing is, but how two things interact. And the property of one thing are the way it affects the other things. And that's a way of viewing quantum mechanics called relational quantum mechanics, which I, in particular, defend on that book. So out of this mystery of quantum mechanics, of the various ways of trying to make sense of it, I describe in detail this relational interpretation, which tell us that the world is not made by things with properties, but by things that interact with one another, and they have properties only when they interact. Relations, rather than properties, things and properties.
And the relations are intimately connected to observations, which again, it's a trivial example, but Aristotle made an observation that these fish that were thought to be fish, giant fish, were actually mammals. And they nurse their young. They have lungs and blowholes or whatever. I'm not an ichthyologist or a Balaenologist studying whales. But one thing that stood out for me, first of all, whenever I see a book nowadays about quantum mechanical interpretations, I had David Kaiser on. We've talked with Adam Becker, many books. Sean Carroll's been a guest many times. And it's I always get this sensation that, oh my gosh, not another quantum interpretations book. And that has an acronym I've coined called NIQWAB, which in Arabic means very wise or learned. So I want to salute you for being a NIQWAB, very, very wise and learned. But when I read about quantum mechanics, I always think, are these kind of, how do I translate it into today's language? So today, there's a war going on and between proponents of string theory, for example, lying at the heart of quantum gravity, maybe theories of everything. There are proponents such as yourself, Lee Smolin, and others, although we'll talk in a different segment about how Lee is maybe becoming a little disillusioned, but we'll talk about that later. But nevertheless, I try to translate it. We're the camps of Schrodinger, and Heisenberg in opposition, the same way that people in string theory like Michio Kaku, past guest on the show, and yourself might be in opposite camps? Are you dueling? Is it kind of that rivalry that we should think about, where there will be only one victor, or is it not a zero-sum game where both Heisenberg and Schrodinger are correct? Do you see any possibility for that to occur in, say, string theory versus loop quantum gravity?
Are you asking about Schrodinger versus Heisenberg, or are you asking about loop versus strings?
I want to say, is the tension between loop quantum gravity and string theory reminiscent or rhyming with the history of Schrodinger versus Heisenberg? Those are two diametrically opposed, but ultimately harmonious relations. But is string theory reconcilable with loop quantum gravity, or is only one theory going to prevail?
There have been attempts to combine the two and to see the two as different possible different aspects of some larger correct theory. And I don't think this is impossible. Maybe there is a larger point of view, because in loop quantum gravity does not address the problems that are addressed by string theory, namely the unification, the idea of that all the forces should be as aspect of a single thing. So from the point of view of quantum gravity, these are not problems that are addressed. So I don't have an opinion, if you want. I don't have a strong scientific opinion about those problems. And vice versa, from the point of view of string theory, in spite of a lot of progress recent, I would say that the real problem addressed in loop quantum gravity, which is understand the quantum nature of space-time, has never been really addressed so far. I mean, people talk about that and recognize it, and tries to goes around by putting theories on the boundary, theories of the bulk, and things like that. But if you ask the string theory what happened here in the very, very small of the Planck scale, he has no answer. While loop quantum gravity has an answer, has a tentative answer, because we don't have an experiment yet, but there's an answer. There is a very precise theory of quantum gravity in here, in the small, just the quantum aspect of space-time. So could it be that there's a larger theory which is like loop quantum gravity when you describe space-time and like string the unification? It could be. But Brian, everything could be. That's not very interesting what could be. It's interesting what we can do today. And I don't think today the question is what is the ultimate theory of nature. I have never been interested in the ultimate theory of nature. I'm interested in solving problem one by one, right? I'm interested in what happened to a black hole at the end of the evaporation. And I can compute it. I am computing it. Maybe I'm wrong, but I'm computing it. I'm interested in what happened at super short scale, and we are computing it. These are problems that can be solved on the basis of our current knowledge, general relativity and quantum mechanics. And that's what loop quantum gravity does.
And so when we look at the kind of tension between the Schrodinger interpretation and the Heisenberg interpretation, matrix mechanics, wave mechanics, you go into great depth about the kind of beautiful tension between the two, but the ultimate harmony, reconciliation, and union in some sense of the school that says shut up and calculate versus those that say we have to obsess about the interpretations. Yeah, and then, but I look at things like matrix mechanics in a different light now. And again, this book is written not just for the general public, although anybody with an interest and a time to put it in will appreciate this delightful book. But certainly my colleagues and I appreciate it because you make the point that Heisenberg really came out of the same milieu of classical mechanics, Poisson brackets, Hamiltonians, and so forth. So I view it as, and you give this wonderful introduction to commutation relations. So you show it on the page here, and we'll put the equation. Famous, I think it's on Heisenberg's tombstone, right? This equation, the commutation relation, that they don't commute, that momentum and position don't commute. And I think that is the fundamental essence of quantum mechanics.
I agree.
And I really appreciate it after this book. But I want to ask you, the presence of imaginary numbers plays a much bigger role in quantum mechanics than classical mechanics. It's almost like we have to translate into the complex universe to comprehend it. And there's no surprise that we can't understand it because we can't visualize what a quantum... Now, I've always wanted to ask you this. In the wave mechanics of Maxwell, there are imaginary numbers and we have complex numbers. How come that is not, we don't have books about interpretation of Maxwell's equations? Why is it that the presence of an imaginary number in quantum mechanics causes so much more difficulty for the human brain, our consciousness, than the presence of an imaginary number in a classical mechanical field like electromagnetism or regular ordinary relativity?
Let me answer to various things you have said, Brian. First of all, thank a lot for what you have said about my book being of interest to a person like you, namely to a real scientist. Not, I have a strange experience with my books. They are loved more by the extremes and less by the middle. Namely, the people who react with more excitement to my books are those who know nothing about science and have a story which says, look, this is interesting because this happened, this happened, this happened. And as you say, I never try to cheat, but I take away a huge amount of things. I don't talk about that, I don't talk about that. So I just give the core. And those who know science very well, like you work your dirty hands with science, read the book and say, that's an interesting take on that. So it's a perspective. This is interesting by itself. In the middle, there are a lot of people who know some science and look for popularization book for adding more details, and then they get disappointed because they don't find what they have studied. And they say, oh, come on, but I studied at school that this so-and-so, and this book doesn't say that. What's the point? Okay? So I get the criticism from the middle. And I got the biggest praises from my grandmother, who doesn't know how to do 5 times 7, and from a Nobel Prize, who I'm not going to name here, who is an enemy of mine. And but he was excited about the book. So that's exactly what my books, in a sense, are different than the standard popularization book.
Yeah. Well, Carlo, there's I'm Jewish, and there's a Yiddish proverb that he who stands in the middle of the road gets hit by both sides of the traffic. There's probably an expression too, right? So you should apply. If it appeals to everybody, it appeals to nobody. And I love that about your books. I learn something in every time I read your books. And I've read them multiple times.
I love you say that. You're very kind. Now, let me talk about Heisenberg and Schrödinger. The formalism that they introduced, which are completely different, turned out to be aspect of the same story. That was a remarkable. It was Schrödinger who realized that first. So in a sense, they were doing the same mathematics, but the physical interpretation was going on was completely different. And they fought at the beginning. There was even some bitter exchange between the two, in particular between the two camps. The camp which was in Göttingen, Heisenberg, but also Max Born, Jordan, and all those people, and to some extent Iraq in the UK, and the Schrödinger camp, and Einstein was on his side. They had a very different view of what they had discovered. And to some extent, we're still there. There are some people who think a la Schrödinger, namely it's a big wave. It's just everything waving. There's no particle. It's just a wave. And the particle, for some strange reason, the particle end up being manifesting with itself as a wave. And that's the Schrödinger camp. And the Heisenberg camp, still today, are people which in various ways, right, cubism or relational quantum mechanics, perspectival views, other perspective, think, no wave. The wave is just you're doing calculations. There's no wave there. There is a particle that at some point hits something, and there the particle is in a point. And Schrödinger himself, which was the other camp, Schrödinger shifted camp. At the end of his life, he said, "Okay, I was wrong," and said, "No. An electron is not a wave. It's just a particle, but not a continuous particle. A set of discrete interaction. It's like snap, 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 snap." That's what an electron is. This basic discreteness of the manifestation. Max Born had the same intuition. Heisenberg had the same intuition. And I think many physicists don't have that intuition today, and I think this is misleading. It's much better to think of quantum mechanics as manifestations of one piece of the world with respect to another piece of the world, instantaneous. So you are, Brian, the way you affect the world. You are what I see you. I am the way I affect the world. An electron is the way it manifests itself to something else. Everything which is only because it's in relation with something else. The world is it's a network of relations, not an ensemble of things. So you see, in reality, it has not been resolved, the tension between Schrödinger and Heisenberg. We are still in the middle of the discussion and bringing argument to one intuition or the opposite intuition. Yeah. But that's great, because let me say one last thing. Because you said, good. You said, why do we are so confused about quantum mechanics, the eye, the Maxwell equations? You can write also them with the eye, and we are not confused. But wait, you and I are not confused, but Maxwell was. And at the time of Maxwell, there was a huge discussion. What the hell the Maxwell equation mean? Maxwell thought that this was an effective description of a mechanical gears inside the aether, and try to make up with these mechanical models of what happens inside. And it was very slow. In fact, it took only at the time of Einstein, I think. So 40 years later, it became clear, as a physicist said, the Maxwell theory is just the Maxwell equations. Namely, forget the gears, forget the aether, forget all that. Just keep the electric field and the magnetic field. You don't need anything else. You don't even need the space-time in which they're sitting. That came with Einstein and general relativity, right? So the discussion about the interpretation of the Maxwell equation has happened, but we have converged to one view. I think if you and I sit down, I think, what is for you the Maxwell equation and what I have for me the Maxwell equation, we have the same intuition. We know what we're talking about. Maybe we use different words, but we understand one another. And it takes time. It took 40 years. The quantum mechanics is much more radical a jump, but I think we will end up agreeing to a new vision of the world. And the Maxwell equation changed our picture of the world, right? Before it was particle with forces. And now after Maxwell is fields. We have this idea of fields. It's a big jump. But the jump from classical mechanics, things with property, to quantum mechanics, relations between things, is much bigger.
Yeah, and you mentioned, that's beautiful. I always joke with people, imagine if Twitter existed when Maxwell was coming up with his mechanical analog. So he would have said, here are these four equations, and Heaviside would have, promoted them and everything. Oh, this is brilliant. And then he would have said, and the interpretation is gears and vortices and whirls and ether. And people would have said, you're nuts, it's crazy. And they would have thrown away Maxwell's equations for 50 years or something like that. So that's a warning about Twitter and about social media, and you stay away from it mostly. I'm more involved in it lately, but I want to talk about social media, and this is provocative. But you mentioned networks, you mentioned connections, and the matrices of Heisenberg are another way of expressing a network effect. So you can put the two particle interactions, but you could also have your friends and my friends, and we're friends on Facebook. We're not friends on Twitter. I don't know why, but we're friends on Facebook. I'm going to become
a friend of yours so immediately to you.
Okay, that was a shameless grovel for that. Okay, but imagine all of our friends, my friends go across the x-axis, your friends go across the y-axis, and then we look at all the different pairs of combinations, right? So that network, because the matrix is symmetrical, what happened? Your friend of my friend is the same as my friend of your friend, like that. But there's also an aspect of entropy. In other words, the number of connections grows as the number of particles or friends squared. So it grows very fast, but the cost kind of grows as the number of friends. Like you don't have to spend twice as much energy when you have square root of 2 more friends added or whatever that means. But there's an aspect of entropy. There's more ways for, friendships to grow. And it made me think in your book of, maybe Heisenberg actually did more than he realized. In other words, there's an entanglement. Once you have the matrix, you have an opportunity for entanglement, for entropy. And for things to propagate at large distances. Unlike Schrodinger interpretation, you don't have that. You don't have entanglement inherently in it. So I wonder, is that an aspect of superiority of the Heisenberg approach? In other words, that he basically presaged and thought about things like entanglement decades before it became fashionable as it is now?
Yes, not because in the Schrödinger picture it cannot be done. Of course it can be done because mathematically they're equivalent.
Yes.
But because the Schrödinger picture based his it's sorry for the ringing phone. I'm not in my house, so I cannot control it. I hope somebody's going to answer. In the Schrödinger picture, the fascination, that the appeal of the Schrödinger picture is because it's a function in space. And entanglement is that in reality it's not a function in space because it has two legs in different points. So in a sense, Schrödinger picture is that try to hide it. And when you try to make it explicit and make it details, you get too many worlds, you multiply the worlds, you add a lot of stuff to reality. Well, in the Heisenberg way of viewing things, as you're saying, is just relation and connection. And I think your analogy is very good because I think it's the fact that the reality it's not properties of things, but it's connection between things, is a deep reason for which what counts in reality is the complexity. Combinatorial. It's something absolutely incredible, right? You know the fable of the king to whom the wise man who invented check asked as a prize to get one grain in the first, and then two, and then four, and then the king said, "Of course, it's easy." And then they do the calculation, and all the wheat of the empire was not sufficient for that. Why? Because when you do exponential, the number go super greatly. So when you do combinatorics, number goes super greatly, and that's why reality is so complex around us. That's why there are mountains and brain and animals and sea and wind and trees and galaxies. Out of what? Out of electrons, new protons, a few quarks, just a bunch of things. How can you make so that complexity, interactions, networks? That's what reality is. It's a network. It's a complexity. It's the richness of the way things combine themselves. Not how things are, but how they get together.
That's so beautiful. And I think about that too. And I think about my friends that, are more hermits and isolated. Maybe they don't want families. Maybe they don't want to, find a partner. I think, the number of connections, the combinatorics explodes faster than the cost increases. In other words, if you have 2 kids and then you have 3 kids, you don't need another house. You can live in the same house, hopefully. But the number of connections between the 2 of them and the 3 of them and the 4 and all of you together, that grows exponentially fast, as you just pointed out. I think that's beautiful. And so I use that to advocate for bigger families, bigger friendships, and it doesn't even have to be biological. I feel connected to you, as we're going to get into.
Instead of fighting one another and saying, "Oh, that country is becoming too powerful, is our adversary, our enemy," let's make connections. It's better.
Absolutely. And the most impressive, beautiful quantum device ever invented is our brain, right? Is whatever's happening in our brain, which you touch upon in consciousness in this book. I never like to give the end of the book away, but it is so beautifully written. It's such poetry as well. And I think that applies. There's always an old joke that my colleagues will talk about, we want to teach, physics for poets. And I actually taught a class with a Pulitzer Prize winning poet, Ray Armantrout. And she and I taught poetry for physicists, because I think they need some of this. They need the Shakespeare. They need the Tempest. They need to be the feeding of the soul for what else is there, as you say, too short the life. And for me to think about, what invests the quantum mechanical reality with meaning, it's the human connections. And so therefore, I salute this wonderful book called Helgoland, the story of one of the most delightful, mysterious episodes in cosmic history that led to a revolution in our understanding. Carlo, thank you for coming on to talk about this wonderful new book.
Thank you very much.
Any sufficiently advanced technology is indistinguishable from magic.